In this video, we're going to take a look at section 2.4, which is on operations with functions. So what we're doing in this section is we're taking the concept of a function and considering them as a group of mathematical objects, much like numbers, right? So we think of numbers as a group of mathematical objects, like 1, 2, 3, 4, 5. And then we define operations on that group. For numbers, we've defined the operations of adding, how you add two numbers together, what that means, subtracting, multiplying, dividing, and other various things like square roots, stuff like that, right? So we have all these operations that we can apply to that group called numbers. We want to do the same thing with functions. We want to think of functions as a group of mathematical objects, and then we're going to define operations on that group. And so we're going to have this collection of equations. Now remember, functions have that special property that when you choose a number for x and you plug it into the equation, it only gives you one answer for y. That's what makes an equation a function. And so we're going to consider all equations that have that property to be in this group. And then we're going to define some operations on that group. And so it turns out that you can do with functions a lot of the same things that you can do with numbers. So for example, you can add, subtract, multiply, and divide functions. And the main point that I think often gets overlooked in this material is that when I add two functions together, like I'm doing here, I get another function. You get something that stays in the same group. So when you add two functions together, so you're taking two things from the group of functions, adding them together, you get a result. That result is guaranteed to be in that same group of functions somewhere. Same thing with subtraction, multiplication, and division. So this concept is called closure. I might have talked about, I'm trying to think what topic that comes up in, I guess with imaginary numbers, right? So again, it's not always guaranteed that when you add two of the same, you'll get something of the same. And the example I gave previously was odd numbers, right? When you add two odd numbers together, the result is an even number. So odd numbers do not have this property of closure. When I add two odd numbers together, I don't get another odd number. It doesn't stay as one of the same. It becomes a different, it comes from a different group, right? So the result of adding two odd numbers together is a number that is from a different group. It's from the group of even numbers instead. So it's a thing that's not automatically guaranteed, and I'm not going to prove it for you here for functions, but I'm telling you that functions have this property of closure. When I add two functions together, I don't have to vertical line test the result. I don't have to do, experiments by checking and plugging in numbers. I don't have to look at a table of values to see if x is being repeated. All the stuff we talked about in 2.1. I don't have to do any of those tests in 2.4. I know that when I add two functions together, the result I get will be another function. It's guaranteed. And again, same thing for subtraction, multiplication, and division. And so we have these special notations for the new function that we're getting. So when I add two functions together, f and g, the result I get will be another function, which I label with the function notation f plus g of x. So I give it the special label to indicate that it's a function and to also indicate the origin of that function, how we arrived at it, right? We arrived at this new function by adding f and g together. F of x minus g of x is f minus g of x. That's the label we give the new function that we're creating. F of x times g of x gives us a new function which we label f times g of x. And f divided by, I'm doing it backwards here, f of x divided by g of x, if I divide those two functions, I get a new function that I label f over g of x. All right, and so let's practice finding some new functions using these operations. So for the first couple of problems that you'll see, they're trying to make it easier. Again, I hesitate to use the word easy in any topic in college algebra because it's not, I don't think any of them are necessarily easy, but some things are easier relative to other things. So they're starting off with the easier version of this type of problem by giving us a number to plug in. So we're not going to be getting another function with these problems. if they're giving you a number to plug in at the beginning, then your answer will just be a number at the end. So we're just supposed to get a numerical answer here based on this notation. Right, so here we have f minus g, but instead of x, we have of negative 8. All right, so f minus g, whoops, oh, it's still giving me a hard time. Sorry about that. There's a, I don't know if you can see it, there's a little button on this pen. I don't know if you can see it if I hold it at an angle. I can't really tell on my feedback monitor if you can see that or not, but it really gets in the way. It's hard for me to hold this pen without somehow interacting with that button, and the button erases. So when I hold the button down and mark, it actually erases what's there instead of writing like I want it to. And so I don't know how to disable that feature on this writing tablet. Anyways, I'm getting off track. So f minus g of negative 8. Now it looks like you're distributing. Like if you go back to this, it looks like, oh, you're taking the x and distributing it into the parentheses. It's not. It's not distribution, because the distributive property is a result of multiplication. This is not multiplication. This is function notation. It's not multiplication, even though it kind of looks like it. So I would really be, I don't know, I've never seen this mistake, but for whatever reason, I'm paranoid. I'm nervous about students thinking of it this way. Because if you think of it as distributing, you might say, okay, f of negative 8. And then you might say, okay, negative times a negative is positive, so it'll be plus g of 8 or something like that, which is incorrect. These are not being multiplied. We're just merely applying the definition that f minus g of something equals f of that something minus g of that something. That's all we're doing here, right? So the definition of what this notation means is that I want to find f of negative 8 minus g of negative 8. Right? And to find f of negative 8, this is something we studied at the beginning of chapter 2. You want to take f of x, which is given in the directions up here, and plug negative 8 in for x, right? So instead of x, we have negative 8. And so that's what we're going to plug in up here. So I don't know if I have enough room here. So I want to find f of negative 8. That means I want to replace x with negative 8, which is what I'm going to do on the right-hand side of this equation. So I'll get negative 8 squared minus 10, which is going to be 64 minus 10, which is going to be 54. And a common theme in this section is substitution. Taking the function notation out and replacing it with what it's equal to. We're going to be doing that on almost every single problem in this section. So once you've determined what the function equals, take that function notation out, replace it with the thing that it's equal to. So f of negative 8, we just found out is equal to 54. So take out f of negative 8, replace it with 54. And we'll do the same thing with g of negative 8. So we'll do that down here. So g of x is equal to 3 minus x. So g of negative 8, we replace the x with negative 8. We get 3 minus, replace this x with negative 8. Negative of a negative is positive, right? So this will be 3 plus 8, which is going to be 11. So now that I know what g of negative 8 is equal to, I take the g of negative 8 out. I replace it with what it's equal to, which is 11. And then I'll copy down the minus sign, and I want to subtract those two results. So 54 minus 11 is going to be 43. And that's the answer. So f minus g of negative 8 equals 43, and that's what you would type into the box. All right, why don't you give this problem a try? So with these problems especially, they go fairly quickly, and I think they're pretty, like I said, they're the easier version of the problem. Hopefully you've kind of caught on to how that works. This one's kind of written on a single line, so it's written out horizontally, but we have here f over g, if we want to write it out this way, of negative 10. So pause the video, see if you can identify what that's equal to, and then resume the video to see if you came up with the right answer. All right, so what you should be coming up with here is f of negative 10 over g of negative 10. So I need to find f of negative 10. I should have paused my recording and just did this work off video, but I didn't think to do that, sorry. So it's going to work the same way as this problem over here. We use the definition of what this notation means. It means this. So I need to find f of negative 10 and g of negative 10. I'll do that over here using the directions. Now this time f of x happened to be the same as the first problem, but g of x is different, so be careful about that. And so we're going to get 100, because negative 10 squared is 100, minus 10, which is 90. So now that I know what f of negative 10 is equal to, I replace it. I'm going to replace that with 90. We'll do the same thing with g. So g of negative 10 will be 9 minus negative 10, which is going to be 9 plus 10, which is going to be 19. Now that I know what that's equal to, I replace it with what it's equal to, which is 19. And I get 90 over 19, which, since it's a fraction, you want to reduce it, but these numbers do not reduce. On your homework, you might get numbers that can be reduced, and in that case, you should reduce your fraction. Right, but in our case, it can't be reduced, so that's our answer, 90 over 19. All right, let's take a look at this sort of transitional problem. I don't know, this might actually just make things more confusing. I might just need to cut this out in the future whenever I get back to revising my homework problems and my lessons. Here we have f times g of d. So it's not x, but it's not a number either. So if they don't give you a number to plug in here, your answer will not be a number. So I've in the past had students feel a little confused about what is my answer supposed to look like? Is it supposed to be a number? Is it supposed to be an equation? And that's how you tell. If they're giving you a number to plug in, your answer should be a number. If they're giving you a variable there, your answer should be an equation. So this time we're going to get an equation as our answer to type into this box. But we're not going to use the original variable x. We're going to use a new variable d. So f times g of d, if we use the definitions we saw on the screen a couple slides ago, this is supposed to equal f of d times g of d. All right. So what does f of d equal? Well, f of x is x minus 3. I want to replace the x with the letter d. So really, I'm not even changing the equation, which is what's kind of confusing about this. It's the same equation. It doesn't look any different. I'm just using a different letter for the variable. That's all this is doing, is saying instead of using your x as your variable, let's use d as the variable. Let's just give it a different label. But otherwise, it doesn't change anything. But once I've identified what f of d is equal to, I take the function notation out. So even though I don't have a number, I still follow that same principle. Once you identify what the function is equal to and have it as simplified as possible, you take the function notation out, replace it with what it's equal to. F of d, as simple as I can make it, is equal to d minus 3. So I take f of d out, replace it with d minus 3. I'll do the same thing with g. So g of x is, let me just try rewriting that. G of x is x squared minus x. So g of d, I just replace all the x's with d's. And so I'm going to get, instead of x squared, I'll have d squared minus, instead of x, I'll have d. And again, that's the best I can do with that. I really can't simplify that any further. So I now am ready to substitute. Take g of d out, replace it with what it's equal to, which is d squared minus d. So I'm replacing the function notation with the thing that it equals. Then I want to multiply these two together, and maybe you might have been 2 steps ahead of me on this, but I waited to address this. Since these have 2 terms, and this one has 2 terms, I don't know why I said these, but this one has 2 terms, and this one has 2 terms, and we want to multiply, we need to use parentheses around these. All right. And so you could have added that in already, but I decided to wait. Now I want to multiply these together, and because it's 2 terms times 2 terms, you're going to use the FOIL process. So we're going to use FOIL. What's a good color to use here? I guess green. I haven't used that yet. So first, outer, inner, last. To multiply these together. And unfortunately, you might say, do I have to? Yes, I believe if you type this in as your answer, MathXL won't count that correct. It wants you to actually multiply it out and simplify it. So we'll get d times d squared, which will be d to the 3rd power. D times negative d, which will be negative d squared. Negative 3 times d squared will be negative 3d squared. And negative 3 times negative d will be positive 3d. And you might not be sure if that would happen, but it does turn out that you get like terms in the middle. So combine those together, you get d to the 3rd power minus 4d squared plus 3d. And that's as much as I can simplify it. And that's my answer. So that is what g times sorry, I said the wrong letter, f times g of d equals, right? So this is equal to this. All right. Okay, let's take a look at the next one. So these are I would say, I don't know, in a way they're easier, but they're also more abstract, and so it can be a little more challenging for students to figure out. So I would say these are the harder variants of these problems, where instead of having a number or a different letter to even plug in, it just wants you to leave it as x. And so we're going to be getting an equation as an answer here, right? F minus h. Not only that, they're being a little bit lazy with this. Not that it's wrong to write this way, but the full notation would be f minus h of x. But since x isn't being modified in any way, they're not even mentioning it. So they just put f minus h. And it's implied that it's f minus h of x. Because if it was going to be something different, they would have written it there, right? Like on the last problem. So we want to find f minus h of x. That's going to equal f of x minus h of x. Now here it's even easier than the last problem because there's nothing for me to plug in. There's nothing for me to modify, to simplify. So I just jump right to the substitution. Take the function notation out, replace it with what it's equal to. Right? F of x, since there's nothing for me to do, I'm just going to go ahead and take f of x out, replace it with what it's equal to, which is the square root of x. And do the same thing with h of x, right? There's nothing for me to plug in, there's nothing for me to modify, so I take h of x out of this formula, replace it with what it's equal to, which is 1 over x minus 7. And then I want to subtract these two, so I'm going to put a minus sign between them. I'm going to try to put a minus sign. All right. And then you want to simplify just like we did on the last problem, but there's nothing to really simplify here. We have a radical, we have a fraction, we're subtracting them, you'd have to get a common denominator, it would become very messy, and nothing really would simplify, nothing would combine together or look any better. So in fact, we're actually done. So like I mentioned, in a way, even though this is more abstract, it's really easier because there was nothing for me to plug in. And then after I did the substitution, there was nothing for me to simplify. So I'm just done with this problem right away. This is the answer, as scary as it looks. And again, what's amazing is that we know that's a function. No matter how bad that looks, I know it has to be a function because of how it was constructed. If I'm subtracting two functions, the answer has to be another function. So this is a function. I don't have to graph it and vertical line test it. I don't have to experiment on it by plugging numbers in to see how many answers I get for y. It's guaranteed to behave as a function. It's a function. All right, and that's the answer. Right? So f minus h is equal to this equation here. Now, there is another part to this problem, which I think is going to be a lot more challenging than this part was, finding the domain. But I haven't talked about how to do that yet, so let me talk about that first, and we'll come back to this problem. The domain of f plus g of x, f minus g of x, and f times g of x is just the intersection of the domains of f of x and g of x. So to find your new domain for your new function, all you have to do is find the domains of the original functions and then look where they intersect each other, which is this symbol here. I shouldn't put the word or there, which is also an and, right? You're trying to find where they overlap, right? So maybe I should just put that instead, right? Because I'm referring back to like the inequalities that we did back in chapter 1. But let's just go directly to what is relevant here, which is you want to find where the original domains overlap each other. That will be the domain of your new function. Now, I'm singling out the division one, f divided by g of x, because the domain for that one is still the same. It's still the overlap of the domains of the original two functions. But you have an extra thing to consider, which is you don't want to choose any values for x that would make you divide by 0, right? Because this is equal to f of x divided by g of x. I don't want the denominator to equal 0. So I have to, in addition to finding the overlap of the original domains, I have to remove any values of x that would make me divide by 0, because now g of x is my denominator. When g of x is by itself, it's okay to equal 0. There's no issues there. But when it becomes the denominator of a fraction, it's not okay to equal 0. So we have this extra removal that we have to do. Any numbers that would make the denominator equal 0 have to also be removed from the domain, and then whatever you're left with is the domain of your new function. All right, so let's go back to this one. What is the domain of this new function? So I want to find the domain here. To find that domain, I'm going to go back to my original functions, find the domains for these first, and then look for where these two overlap each other. So where do they overlap? That will be the domain of my new function. And here's how I go about determining that. So for f of x, you should know this one. Now, I get a lot of students, I get a little disappointed because we just talked about this in section 2.3. Square root functions. That was a family of functions that we talked about in the previous section. And so you should have that graph memorized. And if you have the graph memorized, you should be able to pretty easily figure out the domain for that function by thinking of the graph. So the way I get the domain for this one is I think about, I do this in my head, but I visualize what that graph looks like. And if you're not there yet, you need to get there soon. You want to memorize square root of x, what that graph looks like, x squared, and absolute value of x, right? Those are the three families that I focused on in section 2.3. And you need to memorize those graphs in order to use those methods in 2.3. But it also ends up being helpful here, right? So the graph looks like this, right? Starts at 0, 0, and it's a side. Remember, it was the confusing one to describe. It's half of a sideways parabola, the upper half, right? So it looks like this. And I don't need to draw it in any better detail than that to figure out the domain, because remember, the domain is how far to the left the graph goes, how far to the right. So how far to the left? It goes as far to the left as 0. How far to the right? It goes to infinity. Right. So the domain of f of x is 0 to infinity. What about the domain of h of x? This one we have not discussed graphing yet, but we will. So notice I said the word yet. We will talk about graphing these functions at the end of chapter 3. They are fairly challenging. They involve things called asymptotes, and it's a pretty difficult kind of graph to put together with all the details that are relevant. So you might say, well, how am I supposed to find the domain if I can't figure out what this graph is yet? You don't need to use the graph to figure this one out. You can just look at the equation, right? What number could I not choose for x? I just talked about it on the previous screen, actually, right? If you have a fraction, you don't want to divide by 0. That's the issue you have to be concerned about. So I look at the denominator, and I don't want this to equal 0 because then I'm dividing by 0. So what number for x would make this equal 0? 7, right? I don't want to plug in 7 for x because 7 minus 7 is what would make me get 0 in this denominator. And 1 divided by 0 is undefined. It's broken. It doesn't work. It produces no results. So we cannot use that value for x. X is not allowed to equal 7, but otherwise, any other number here should be fine. It doesn't give nice answers. You might say, well, if I plug in, 1 for x, I get negative 1/6. That's not a very nice number, but it still produces a number, right? It's not a nice result, but it still gives a result for any other number of x. The only number that does not produce a result is the number 7. If I plug in 7 for x, I get division by 0, and that just ruins everything, right? It doesn't ruin everything. It just ruins that situation. So this is my domain. It's all real numbers. And you can write this in interval form, but I'm not going to bother going through that exercise. We'll just write it out in words. The domain is any number but the number 7. All real numbers but 7. That's the one number you're not allowed to use in that function because you would divide by 0. So to find the overlap, I recommend graphing the domains, not graphing the equations, just graphing the domains on a real number line, like we did back in chapter 1 for inequalities, right? So because the domain is concerned with just the x values, you can fit that information on just one axis, which you can think of as the x-axis, right? So I'm just thinking of, I don't know if I want to get into like other ways of thinking of it, but just since it's a one-dimensional set of numbers, you can graph that set on just a real number line, and you don't have to think of it as the x-axis. That maybe is a little bit confusing, so I apologize for that. But you can graph these on a real number line, and that would be a good way to see where they overlap each other. So for f of x, that's 0 to infinity. So I'm going to start at 0, put brackets because we have brackets in the interval here, and all the way to the right forever, right? So this is the domain of f. For the domain of g, it's every number but the number 7. So I mark 7 on the real number line. And then in order to skip over it, because that's the number I don't want, I want to skip over the number 7, a convenient way of doing that is to use an open circle. Right? And then I shade everything else in. Everything to the left of 7, everything to the right of 7. Just the number 7 itself is being omitted here. Right? And so that would be the domain of g. So where do we see them overlapping each other? They overlap here from 0 to 7, and then they overlap from 7 to infinity. Right. And so from 0 to 7, we see that the two domains are, I don't know what I was doing. I went into autopilot there without really thinking about what I was writing. 0 to 7, right, would be this segment here. This segment goes from 7 to infinity. Notice I'm using parentheses on the 7 because I want to skip over that number. I don't want to include it. So I don't want brackets on the 7. I want parentheses there. But the 0 is included because they overlap at 0. They both domains contain the number 0. So we keep a bracket on the 0, but we want to skip over the number 7. And then we do a union to connect those two together. And so that would be the domain of my new function. I don't feel like rewriting it down here, so I'll just keep it over here, and that'll be the domain. Okay. So that's how you find the domain of these new functions you're creating. You go back to the original functions where they're simpler, find the domains of those individual functions first, and then look for where they overlap each other. Wherever they overlap, that's the domain of your new function. And if you're dealing with the function where it's f divided by g, additionally, you should remove any numbers that would make you divide by 0. So you do the overlap like we did here, and then you would look for any numbers that would make the denominator equal 0 and remove those from this result. And then once you've removed those numbers, then whatever's left is your domain. Okay, and that's only for f divided by g. All right, so that's domain. Now, I have this, I keep meaning to, I should have changed it today before I recorded the video. There's weird typos on this. I, again, must have blanked out when I was typing this out because this is horrible how I typed it. So let me rewrite that. New operation, composition. And this is the way it should be written. I don't know what I was thinking. It should be, I guess this part's actually correct, but it's missing the of x, right? If you want to put parentheses around that, it should be because you're writing it in function notation and there should be an of x part there. And then this part, I guess, is not so horrible, except I just have an extra set of parentheses. Not even an extra set, just this should not be here. So it should be f of g of x. So I got a little carried away with the parentheses, so it should just look like this. So this is what I meant to type there. This is composition. I'm calling it a new operation because this operation does not exist with numbers. So with adding, subtracting, multiplying, and dividing, we're familiar with those operations because those operations exist with the set of numbers. But composition is an operation that is impossible to do with just numbers. And what's essentially happening with composition is you're taking one function and you're plugging it into another function. So you're taking one equation, plugging it into another equation, and you're getting a new result from doing that, which again is guaranteed to be another function, right? So if you're taking one function and plugging it into another function, the answer you get from that is guaranteed to be a function as well. But you can't do that with numbers, right? You can't take one number and plug it into another number. You can't say, let's take the number 5 and plug it into the number 2. It doesn't make sense. So that's why you have not seen this operation previously, because you couldn't do this with numbers. But we can do this with functions. So it's called composition. The notation for it, you got to be careful. It's an open circle, which a lot of students will confuse with the closed circle or the dot, right? So this is a dot here, which indicates multiplication. The open circle indicates composition. And so you need to be careful not to confuse the two. That is a really common mistake. So this is not just my paranoia of a mistake that I've never seen, but I'm always worried students are going to make. This is a mistake I see all the time. So when students are taking a test, they get to the composition question on the test and they multiply the functions together. And even though that might be a lot of work and maybe they're doing that correctly, I can't give you any points for that because you're not doing the operation that you were instructed to do. You're instructed to do composition when you see this notation, and that's a whole different thing. And so I can't give you any credit if you multiply the functions together. All right. So what's happening here is that f composed with g, so that's how you would read this, f composed with g is the function you get when you take g of x and you plug it in to f of x. Notice g of x is inside the parentheses. It's inside the function of f of x. So we're replacing the x in f of x with whatever g of x is equal to. All right, so I know that sounds confusing, but you're saying whatever function g is equal to, take that and plug it in as your x value, or your variable for f of x. I know I'm saying that kind of funny, but and that's how you're getting this new function, which is the composition of those two. So you're taking g and plugging it into f, but as far as like interpreting this notation, you want to rewrite this like this, and you just go in order when you do. So your problem will be given to you like this most of the time. And then to rewrite it in this form, you just go in order, f of g of x. And every time you say the word of, you just put another parentheses. You start another parentheses. And then after you get to x, you close all the parentheses you started. So it's f parentheses, let me say it like this, f of g of x, close parentheses. So that's how you translate this into something that you can work with. And then once you have it in this form, it's kind of self-prescriptive what you're supposed to do there, but it can still be kind of confusing for students. So let's do some examples to hopefully make it less confusing. Again, we're going to go through the same, how do you say, trials? I don't know. We're going to go through the same structures we did with the other operations. We're going to start with just having numbers, and then we're going to work up our way to having equations, right? So as I mentioned before, if they give you numbers to start with, your answer is just going to be a number. And that's what we're going to see with these two problems. Now this one, they kind of avoid using the composition notation, but this is f composed with g of -2. So they could have easily asked the question this way, and then we would interpret this as going in order, f of, so I put parentheses, g would be the next thing, of, put parentheses, -2, and since I got to the end, I closed the parentheses I started. And I get this, right? Now, when there's a number being plugged in, another way, or I guess even if there's a variable there, another way you can think of how to evaluate this is to start from the very inside and work your way out. So going into the very inner parentheses, we have -2. What do I want to do with that -2? I want to plug that in to g, right? That's where -2 is going. -2 is the argument for the function g. So I'm going to take -2 and plug it into g. I do not plug -2 into x. What am I saying? I don't plug -2 into f. So a very common mistake students will make with this problem is they'll say, oh, there's -2, plug it into both of my functions. That is not how this works. So the composition forces you to manage one function at a time. You don't know what you're plugging into f yet. You have to plug -2 into g first, and then once you get that answer, that's what you want to plug into f. So I don't even know what it's going to be yet. So with composition, you can only work with one function at a time. You have to plug a number into one function first, get that result. That result goes into the next function, and then if there's more, you get that result gets plugged into the next function, but you can only do one function at a time. All right, so we're going to use g first. Plug -2 into g. So I'm going to get -2 squared minus 1. -2 squared is +4. So they're really like, I don't know if I just chose the examples really poorly, but I feel like we've had a lot of examples with negative numbers in kind of difficult situations. So be careful about that on the homework. They're probably going to stress test you on that a little bit by giving you a lot of negative numbers inside of powers of 2 after minus signs, just to kind of test your arithmetic ability. I don't know if I said that right. Arithmetic ability, maybe is the right way to say that. Anyways, 4 minus 1 is going to give me 3. So g of negative 2 is equal to 3. We have the result now. So just like we were doing before, same principle here. Once you know what the function's equal to, take the function notation out, replace it with what it's equal to. Right? So in this case, g of negative 2 is equal to 3. So I take the g of negative 2 out, replace it with what it's equal to, which is the number 3. Everything else is going to copy down, so this parentheses copies down, this parentheses copies down, the f copies down. And so you see what's about to happen is the answer we're getting from g is what we plug into f. So it's kind of it's a weird transition, because what we're essentially doing is taking the output from one function, making it the input of the next function. We're taking the y value from g, right? Because g of negative 2, that's the y value, right? So for g, when x is negative 2, y is equal to 3. We're taking that y value of 3, and we're making it the x value for f of x. We're going to plug that in for x in the next function. So that's what's happening with composition. So now that but you don't even have to maybe think of it on that level. Just use that principle. Replace the function notation with what it's equal to. G of negative 2 is equal to 3. Now that I see this, it's clear what I need to do. I want to take 3 and plug that into f. So I'm going to take f of x, and I'm going to replace the x with 3. And so I'll have negative 4 times 3 minus 1. That's going to be negative 12 minus 1, which will be negative 13. Right, and so that is what we get here as our result. So again, it's a little bit silly, but replace the function notation with what it's equal to. So take f of 3 out, replace it with what it's equal to, which is negative 13. There's no other functions for me to plug this into, so we're done. The answer is just negative 13. All right, we're going to do the same thing over here, except these are chained together. We have 3 of them chained together, right, instead of just 2. So with composition, you can actually add as many functions as you want to that chain. I don't think you're going to see anything worse than 3 functions chained together, but you could have more. And so again, I need to interpret this into a more usable form, into a form where I know what I need to do mathematically. Because in this form, it's kind of hard to tell what's going on. So I want to rewrite this in function notation without the circle symbols in there. I go in order, starting with the first function, which is g. So I take g, and then I say of, which means I put parentheses, h, of f of 4. So every time I said the word of, I start a new parentheses. And once you get to the end, which is the 4, you close all the parentheses you started, which is 3 of them. So I have 3 of them to close here. And then you start from the inside and work your way out, right? So you start with the very inner parentheses, which is 4. What does that get plugged into? That gets plugged into f. I don't plug 4 into h. I don't plug 4 into g. At least not to my knowledge, right? I don't know what I'm going to plug into h or g until I have some results first. The first result I need to get is f of 4, right? So I'm going to take function f, plug in 4 for x. So we'll get 5 times 4 minus 7, which is going, I guess I'll just work straight across, which is going to be 20 minus 7, which is going to be 13. Now that I know what f of 4 is equal to, I replace the function notation with that thing that it equals. So f of 4 is equal to 13. Take the function notation out, replace it with what it's equal to. Everything else copies down, so the h copies down, the g copies down, and the parentheses are going to copy down, the ones that are left. So this is the thing that I replaced, right? So a couple parentheses were kind of taken out by this replacement, but we still have these and we still have these parentheses. What's the next step? Now I want to take 13, the answer I just got from f, and plug that in for x in h. Hope there's so many prepositions there. I start to get confused about which preposition should I use where. So I think I hopefully said that in a reasonable way. So we want to take 13, which is the output we got from f, plug that in as our value for x in the function h. Right, so here's h of x right here. I'm going to plug in 13. Now they're doing a little cute, clever thing here. let me undo that equal sign, with these two functions, which I'll explain in just a second. But we're going to plug in 13 for x. It's a fraction, but it's going to work out just fine. And so we're going to get 13 plus 7, which is 20 on top, over 5 on the bottom. 20 divided by 5 is 4. Notice that's the number we started with. F takes the number 4 and changes it to 13. H takes the number 13 and changes it back to 4. And that's not an accident, and that's not a coincidence. That happens every time because they intentionally set these functions up to have that behavior. And it's foreshadowing because the next section, 2.5, is on this concept of what are called inverse functions, and this is exactly what inverse functions do. Whatever f does to change a number, h is undoing it and taking you back to the original number you started with. So h and f are what we call inverse functions of each other. So, and again, that doesn't happen with random functions. It just, they carefully constructed these for that to happen. I wouldn't assume that it automatically happens on your homework, because what ultimately is going to end up happening here, right? We take the function notation out, h of 13, replace it with what it's equal to, which is 4, and now we want to plug that into g. So ultimately, the number we started with here is the number we want to plug into g to get our final answer. But I wouldn't assume that automatically happens on this particular problem on the homework, because that only happens because these are inverses of each other. And if they switch it up on you and give you functions that aren't inverses, chances are you're going to have a different number here than what you started with. Right? It's only happening because these two happen to be inverses of each other. Right? Now I want to find g of 4. So I'm going to take g, I'm kind of out of room here, but g of 4 is going to be 4 squared plus 7. That's going to be 16 plus 7, which is 23. And so, again, replace the function notation with what it's equal to, which is 23. And since there's no other functions for me to plug numbers into, we're done. We're at the end of the problem, and the answer is 23. Okay, so that's how composition works with numbers. How does it work with equations? All right, so let's start by interpreting this. We're going to take this notation and write it in a more usable form. We'll go in order. F of g of x, which really is the actual definition that we saw earlier. So you could maybe even just go off of that. But it's good to understand how that, how that works, because it won't always match what our definition was. This time, we don't have a number to plug into g. And so we would start with that. We'd say, okay, let's start with the, again, start from the very inside and work your way out. So you go to the innermost parentheses, which is x, work your way out from there. But there's nothing for me to do with x, right? It's already an x. I don't need to change or modify anything. So you kind of just skip that step and go out to the next level, which is g of x. Right? So we have g of x here. And just like we were doing before, we want to replace the function notation with what it's equal to. And since I don't have to make any modifications or simplify anything, I'm ready to just do the substitution right away. What does g of x equal? G of x, according to the directions, is equal to 3x minus 5. So we take the g of x out, replace it with what it's equal to, which is 3x minus 5. Everything else stays the same, so we copy down the f, we copy down these parentheses, and now I can see what needs to be done. I need to take 3x minus 5 and plug that into f of x for x. So whatever's here needs to get plugged in for x in function f of x. And it can get a little confusing because we're using the same letter. The variable here is x, the variable here is x, and students kind of get caught up on that. And they think, well, how can this x become this other x? Excuse me, my voice kind of cut out there. What I've begun telling students that seems to be effective, I've been doing it for several years now, but it took me a while to arrive at this way of thinking and explaining, is they're not the same x. Even though they're the same letter of the alphabet, this x here is not the same as this x here. So I think that's where the confusion is. Students think, oh, it's the same x, but it's not. So the distinction I make here is that this x is the live variable x. It's the x that will show up in your final answer. It's the x that you're going to have in your equation. This x is a dummy variable x. It's just a placeholder in this function for whatever we ultimately want to plug into that function. And we could have used any other letter. There's nothing special about the letter being used here. It doesn't even have to be x. We could call this f of, z, which would equal 2z squared plus 3, right? X is just a placeholder here. There's nothing special about it. This x is the special x. It's the live variable x that's in our final answer. All right, and I'm sorry the z's, maybe I shouldn't have chosen. I was trying to think of a good letter to choose. Z wasn't probably not the best choice. Z squared plus 3. All right, so if it bothers you that this x, that we're using the same letter, that we're using x here just like we have in our problem, change this one. There's no reason why it couldn't be any other letter for this function. So change it to a different letter if that helps you get over that confusion. Right? This x is a dummy variable. It's not the same as this x here. And so we want to replace the dummy variable x with the live variable x, which is in the form 3x minus 5. And so everywhere I see an x here for the dummy variable x, I'm going to replace it with 3x minus 5. Right? And so I'm going to end up getting 2. So let me write this down here. Right? So I don't know, maybe this is not the best place to write it. F of x equals 2x squared plus 3. I'm replacing the x here with 3x minus 5. But everything else is going to stay the same. The 2 gets copied down. I'm going to raise this to the second power still. I'm still going to have the plus 3. I should have used different colors there to make that easier to see, but hopefully you were able to follow that. And so this is what we get. And unfortunately, and this is really the final answer. This is the equation we're looking for, but I believe Math Excel will want you to multiply this out to, it says simplify your answer. So I think this is what they want us to do. So we're going to take 3x minus 5 and square it, which remember, you can't distribute the power of 2. We've seen that multiple times so far in this course. I know I know that because I've recorded like chapter 1 and 2 within the last several weeks. So I feel like it's really fresh on my mind. And we've come across this situation multiple times, and I've warned you every time. So maybe I should just stop warning you, because by this point, hopefully you got the hang of that. So you have to FOIL. So you do first, outer, inner, last. You're going to get 9x squared minus 15x minus 15x plus 25. Right. And then I'll go ahead and combine like terms. Right. These are like terms here. And so I'm going to get 9x squared minus 30x plus 25. And then I'm going to copy down the 2. And that 2 still has to get multiplied to whatever this thing is, which is now this. Right? So we still need to put parentheses around it and make sure the 2 multiplies to that whole thing. And we still have the plus 3. So I kind of ignored those for the moment, FOILed this out, and now I'm bringing them back into the picture. Right? So I'll distribute the 2 to each of these. And so we're going to get 18x squared minus 60, and I'm sorry, that's a 0 here, minus 60x plus 50, and then I'll have the plus 3, and then I'll combine those together. And so finally I get 18x squared minus 60x plus 53. All right, and so that is what f composed with g of x is equal to in this problem. See if I can keep that line going straight across. All right. And so that'd be our final answer there. Okay, let's try another problem. So why don't you guys give this one a try. Now this one talks about the domain. Don't worry about that for the moment. I'll give you an explanation for it. It's a little confusing and not really something different math teachers have to kind of emphasize different things. We can't emphasize all things all the time. And the domain of compositions is one of the things that I really don't worry too much about when I'm giving you a test. It might be on the test, but I won't really count it for a whole lot of points. And it's only a question that shows up on a few of the problems on the homework. So it's not really that significant in the big scheme of things, in my opinion. But I'll give you the proper explanation for it, and then I'll maybe give you sort of a shortcut way of thinking of it, and then you can kind of decide what you want to do with that information. But first, pause the video and do this part of the problem. Find f composed with g, and then resume the video to see if you came up with the correct answer. All right, so here's the result you should have come up with. The way you get to that result is you interpret this notation in a more usable form. It's going to be f of g of x. You replace the g of x because that's the innermost parentheses. You substitute that for what it's equal to, which is 1 over x. That is the thing that you want to plug into f of x. So you go to f of x, replace the dummy variable x with the live variable x. So I'm replacing this x here with 1 over x, and I'm using parentheses when I do that. So we have 6 times 1 over x, which we can write as 6 over x. I'm just kind of simplifying it by multiplying those two things together. You can think of the 6 as being over 1, multiply those together, and that's what you get. You don't need to rationalize the denominator here. I don't think MathExcel is going to expect you to do that, so you can just leave it in this form. So ultimately, when you're doing f composed with g, g is getting plugged into f. So some students will kind of skip writing out the function notation and just realize that whatever the second function is, that's what's getting plugged into the first function. So you go to the directions, take that second function, whatever it's equal to, plug that into the first function, and you would still get that result. Right? And that's fine if you want to take that shortcut. Now for the domain, it's complicated, right? Because think about, let me give you another example. Let's say we have f of x equals and g of x equals. How do I want to organize this? One of them I want to be x squared. One of them I want to be the square root of x. Right, and I think this would be the proper way to do this. Yeah, so let's find f composed with g here. Right, that's going to be f of g of x. G of x is square root of x. That's what I want to plug into f. So I'm going to get the square root of x in place of this x here. And that has to get raised to the second power. Right? So what does that equal? Well, that just equals x. Right? So you get x here. Because the square root cancels out the power of 2. And so your final answer is f composed with g of x is just equal to x, which tells you that whatever number you pick for x, that's the answer, right? It's an identity, right? So if I pick x equals 5, the composition is just equal to 5. If I pick x equals 10, it's equal to 10, right? So whatever number I pick for x, that's the answer here for this function. But that's not quite true, actually. So if I were to choose negative 4, for example, if I pick negative 4 for x, this result would seem to indicate that the answer here should just be negative 4, but it actually doesn't ever get to be that. So you can't just assume the domain of this function by looking at the result. Because if we did that here, it looks like any number is fine. I can pick any number I want, and that's going to be my answer, right? But that doesn't take into account the journey, right? Because x doesn't just go from whatever you pick to the answer. It has to go through these functions. So you can kind of think of the functions as like machines, right? Whatever number you pick for x has to go through the machine of g, and it's going to take negative 4 as the input. It's going to do something to it and produce an output. And then that output has to get plugged into function f. And so the machines that these functions have to be able to process those numbers, right? In order to give you that result. And if either of these machines are unable to process the number they're given, then you never get to the result. The machine just breaks down, right? So we have to make sure that whatever number I'm choosing here can go through the machinery in order to get to this result. And negative 4 can't, right? Because what has to happen when I choose negative 4? Negative 4 has to first get plugged into g. What's the problem with that? Right? If I plug negative 4 here for x into g, I get the square root of negative 4. That's going to be imaginary, right? Which means it breaks down. It doesn't work. Because we don't want imaginary numbers with these functions, right? So it never gets there, right? -4 is not even going to pass through function g. So again, if you think of these functions as machines, g can't work with -4. -4 breaks that machine. It never even gives an output to f. So if it can't get through these machines, it can't give you a result. So -4 actually doesn't work here. So what numbers do work? Well, if you think about the machinery, g can only accept inputs that are positive, right? G can only work with positive numbers to avoid giving you these imaginary results. And so we have to start with numbers that g can handle. G can only handle positive numbers or 0. Again, I'm being a little bit too cavalier in my description there. 0 or bigger, right? G can handle any number 0 or bigger. It cannot handle negative numbers. Maybe I should just say it that way. And since g cannot handle negative numbers, we cannot choose negative numbers for this composition because it can't even get past the first function if we do. Once I've made that choice that I've limited myself to just positive numbers, g can handle those numbers and produce an output. And then we have to ask ourselves, does that output, how do I want to say it? Can we take the output and plug it into f? Because whatever we get from g has to be something that can be plugged into f. But f can handle any kind of number. There's no limitations here. I can plug in negative numbers, positive numbers, 0. F doesn't have any limitations. So anything that g could produce, f can handle as an input. Because that's what's going to happen, right? The output from g is what gets plugged in as the input for f. And f can handle any input. So I don't have to worry about f. I only had to worry about g. And my worry for g is that I have to limit myself to only numbers between 0 and infinity. And so that's going to be my domain here. So the moral of the story is that to determine the domain of your composition, you have to take into account the journey that x takes in going from here to here, right? It's not an immediate instant thing. It has to go through these functions. X has to first go through f, and then whatever I'm saying the wrong letter there. X has to first go through g, and then whatever g does with that result, that has to be something that can go through f in order to make it to this result. And so you have to kind of go through that process. So you have to go through that journey that x is going through. All right, so for this function, when I choose a number for x, it first has to be something I can plug into g. So what numbers can I plug into g? Any number but what? Any number but 0. Because it's a fraction, I don't want the denominator to equal 0, so I can't plug in 0 for x here. So my domain already starts off as any number but the number 0. And this is how you would write that. I'm skipping over the number 0 there. Once I've limited myself to that, then g works out fine, right? So as long as I don't pick 0, g is going to be able to handle whatever number I plug into this machinery. Then I have to check to see that I have to think about the numbers that g could produce and if those would be okay to plug into f of x. Right? Now f of x has a square root here, which means I don't want negative numbers. So I have to avoid choosing numbers for x that would cause g of x to come out negative because f of x can't handle those negative numbers. G of x can handle negative numbers just fine. But if it produces negative numbers, then f of x won't be able to handle those results. And then you break down, you don't get to the final result. And so I have to also eliminate negative numbers, right? From my consideration, because if I pick a negative number for x, that's when g of x would be negative. And if g of x is negative, then f of x can't handle that, right? Because if you look at your function here, if I plug in a positive number for x, this comes out positive. If I plug in a negative number for x, this is going to come out negative. And if g of x comes out negative, f of x can't handle that. So I have to eliminate negative numbers as well. And so what am I left with as my domain? I'm left with numbers from 0 to infinity. That's what the domain of this composition is. And that's taking into account the functions that we have to use to go from here to here. Now that being said, that's the same domain you would come up with if you just looked at the final result, right? If you look at the final result, of course I don't want to plug in 0 because then I get 6 divided by 0. That doesn't work. Of course I don't want negative numbers here because I'm taking the square root and I don't want this to be negative. So those same limitations exist in the final answer here. And so I can actually figure out this domain by just looking at the final answer. But that's why I did this example as a cautionary tale. That doesn't always work, right? If you look at the final answer here, it would appear that the domain would be all real numbers, but it isn't. So sometimes those limitations do not manifest in the final answer. You can only find them by looking at the functions. So again, and I'm spending a lot of time on something, like I said, I don't really want to be a big deal for this course. So, it's complicated. It takes a while to get the hang of. And I guess really maybe the unfair thing is there's just not enough practice to really get the hang of it, right? You're only going to have to find the domain for these compositions on maybe 3 or 4 problems on the homework. That's not really enough practice to really get the hang of something that's so nuanced, So I think it's maybe not even really fair that we're asking students to do this. But I still think an interesting thing to think about. What I want to say is that 95% of the time, you're going to be okay figuring out the domain by just looking at your final result. And so you look at this, what are the limitations here? That's going to determine your domain for that composition. But there are going to be a fringe number of cases where that doesn't work, and you only get the right domain if you consider the journey that x has to take through these functions. But so you take your chances, right, by just looking at the final result. But most of the time you're going to be okay doing that. And given the number of problems where this is going to be relevant, I think you maybe, and I'm not normally like this. I'm usually a stickler for, we always want to get the right answer all the time. You've heard me say that before if you've watched all my videos. But at least I think I've said that before. But this is one of the cases I make an exception, where it's like, just go with the thing that's most likely to work and don't worry about the fringe cases where you might get it wrong, because you're not going to see too many of those anyways, because this is not really a big thing in the course, in my opinion. So anyways, last example, and then we're done. Sorry, I hit the 1 hour mark. I was hoping I could maybe keep it under 50 minutes. I almost did it. Now this problem, you'll see a couple of these on the homework, and I put them on the homework because I think they're fun, and because they're like a puzzle, and so I hope that you will enjoy doing these problems and think that they're kind of fun too, trying to figure out. I'm not going to put one of these types of problems on the test. And like I said, there's just maybe 1 or 2 of these on the homework. And the other thing, though, besides them being fun, is that if you do figure these out pretty easily, that means you have a pretty good grasp of how composition works. So if you can do these, I feel like it shows that you have a good grasp of the concept. But I won't put these kind of questions on the test. So they're giving you 3 functions here. F of x equals absolute value of x, g of x equals x minus 5, h of x equals x squared. They want you to use these 3 functions and composition to construct this function. So how would you have to construct the composition in order for the result to come out as this? So what has to get plugged into what, which has to get plugged into what, in order to make the equation look this way? And so they give you some multiple choice options here. So if you think about what's going on, you can see elements of each of these in this problem. But you have to figure out the ordering. That's the tricky part here. So you can see the elements of... What's weird, like my computer just froze up, so I couldn't like move or anything, and my webcam looked like it still looks like it's frozen, even though my cursor's moving now. And I don't know if it's just recording as usual through that, and so I just kind of paused like I'm catatonic all of a sudden. But sorry about that. My computer, it's a new computer, and it works pretty well most of the time, but every once in a while it just like glitches by just pausing for 5 seconds where I can't do anything, and I don't know why it does that. And this is my first computer with a solid state drive. I don't know if that has something to do with it. Maybe that's just a feature of that, or a bug of that, whatever you want to call it. Okay, so what has to get plugged into what to make this happen? Well, we can see we have the minus 5 here, but instead of just x, we have absolute value of x there. So obviously what I want to do is take this absolute value of x and plug that into g of x to replace the x there with absolute value of x. And then that result is getting squared. And so if I want that result to get squared, I need to take that result from this and plug it in to h. That way, whatever I plug in here will get squared, right? So that's what I want to do, is I want to take f, plug it into g to make it look like this, absolute value of x minus 5. And then I want to take that result and plug it into H. So how do I write that as a composition to make sure the plugging in happens in that particular order? You have to write it like this. H composed with G composed with F. Right? You want to start with the first function you want to plug into another function has to go on the right-hand side of the composition. Because remember, you're going to work your way from the inside out. So you're going to start with the innermost function, which will be this one, plug that into the next function, right? So we're going to take F, plug that into G. That's exactly what I want to do here. Take the absolute value of X, plug that into G. And then I'm going to take that result and plug that into H, right? So the result of the composition of these two will next get plugged into H. And you want that to happen last. So it needs to be on the left-hand side. So this is how you would order the composition to create this. And if if that's confusing, again, you can just test out your theories, right? So if you think that's the right answer, but you're not sure, find what this composition is. Go through the work of determining what this composition would equal and see if it matches that. And if it doesn't, try rearranging it, try flipping it around, seeing if that makes you get the right answer. So, venture a guess and then check that guess by actually finding the composition and seeing if it matches the thing you were trying to match. And if it doesn't, try something else. And if you don't find that fun and you don't really care about it and it's not interesting to you, then, you can skip it on the homework. It will count against you. So I sometimes will tell students that, like, well, you can just skip that on the homework. And they're like, well, so I'll still get 100. No, it'll count against you on the homework, but it's only 1 or 2 questions on like a 20 question homework assignment. You'll still have like a 90% on the homework. It'll be fine. It won't hurt your grade. The homework grades aren't going to have that big of an impact on your final grade. As long as they're 90%. I need to be careful how I say that too. You don't want to get all 50% on your homework because yes, that is going to have a big impact on your grade. But 1 or 2 questions on each homework assignment being missed is not going to have a big impact on your overall grade. So anyways, that concludes the video on section 2.4. I will see you in the next video for section 2.5.